Okay, now it is 10 o'clock, 9th of December. I would like to welcome you to the second session of the European Shallow Geothermal Energy Days. My name is Gregor Götzl. I'm working on the Geological Survey of Austria on geothermal energy research, and I welcome you very much to our second session on best practices in shallow geothermal energy use. So I hope everybody can see my screen, and I'm very looking forward for this session. We will have 8 presentations, which would intend to give you a crosscut through the European market on shallow geothermal energy use. We call it from emerging to major markets. We'll have we start with 4 presentations until 11:25. Then we have a coffee break. And then the second part until 1 o'clock, we will focus more on emerging markets, also on novel concepts, on managing shallow geothermal energy use. And you can use the chat function to ask questions to the presenters. We will collect them. My colleague Constanze will forward these questions later on in a short discussion after its presentation. And yeah, I wish you an interesting and fruitful morning. And we would like to start with our first presenter, Dr. Burkhard Sander. I think he doesn't need to be introduced. Most of you know him very well. He was a former president of EGEC for more than 10 years. And he's still in management boards of several European initiatives, such as GeoTRAINET or GeoCOND projects under Horizon 2020 framework. But today, Burkhard will speak about his experiences, his projects in Germany, in Cologne and Bonn region. And I would like to give the word to you, Burkhard, and ask you to present your work. Thanks a lot.
Okay, thank you and welcome. Good to just share my screen with you. Takes a moment, and we'll put it in presentation mode so that you should. No, it's not, now it's in presentation mode, and you should see it in a moment. Okay, what I'm going to do is to talk about some projects with open loop systems, because this is something that's not so much covered in the rest of the sessions. Here, as a start, this means we do not use Boral heat exchangers, but groundwater wells in these cases, and I'll explain a little bit why that's done, depending on the geology. So we have to quickly look at the geological framework in this area. On the right, you see the geological map of North Rhine-Westphalia. By the way, it's nice to have, meanwhile, all this information in most of the German states and in many other European regions available online with GIS servers, so that you really can get to that. And I'm looking forward to seeing more of that, also for geothermal, shallow geothermal purposes from ongoing projects like MUSE and so on. So what you see here is the Rhine Valley, in blue, the River Rhine, coming from the Rhenish Massif northwards to the Netherlands. Netherlands is then up here. And then there is an area where the Rhine, over the many thousands and million years, has sedimented gravel and sand terraces that are filled with groundwater. Looking at the groundwater availability, again, maps from the Geological Survey of North Rhine-Westphalia, you see this large blue area. This is the terraces of River Rhine, a very good aquifer, groundwater layer, but you also can see that here the Rhenish Massif, which is to the east of this structure here, there is not much groundwater. So for a closed loop system with Boral heat exchangers, you would go into that area. But with the this area is making a perfect case for loops. It's also visible here in that map. This is the geothermal yield for Boral heat exchangers as presented by the Geological Survey of North Westphalen. And you see that it's rather good conditions here, and let's say moderate conditions here. This here is something special. It's the area of lignite, of brown coal, open pit mining, where the groundwater level is drawn down very heavily. So we're now going to look at two projects in Troisdorf village here, where the river Sieg is joining the Rhine, and in Bonn. There are numerous other examples, in particular also in the Cologne area, but will, due to the time constraints, I'll just take these two ones. Starting with the one in Troisdorf, the important part here is to start early. And what's on this slide from the Stadtwerke Troisdorf, the city utility, I translated it up here. The local energy transition starts with the development plan. Die Energiewende vor Ort beginnt schon beim Bebauungsplan. I think that's as early as possible to think about including renewable energies, in this case, geothermal, shallow geothermal, in the development plans of the city. And it's something that, for instance, the project RHC-ETIP was working on and has provided some guidance. So that requires local community information and a lot of political activities also. Now to the more technical part. The basic concept here is that what we call the cold district heating in German, kalte Nahwärme. Groundwater in this case is pumped from wells. It's a bit hard to see this production well here. Then it's related to heat pumps in the individual buildings. In this case, it's single houses mainly with the 7 to 10 kilo and domestic, and the cooled groundwater is re-injected into the aquifer. The start of the system was in 2012, and since then it was continuously enlarged, and also new projects in the area have meanwhile been started. So that's the basic concept. To realize such a concept, first you need to know about the exact underground conditions. And for an open loop system, my first, let's say, question always is there a hydrochemical suitability? Is the groundwater quality sufficient for using it for geothermal purposes? Because with a lot of, for instance, iron in the system or so, you'll have some problems to keep your wells and heat exchangers operable over the time. So hydrochemical suitability is the first thing to look at. Then you need to, of course, know the permeability and these exact planning of wells, and the simulation of the groundwater flow in this case was important. No, you should now see it. No, sorry, it's a bit slow once I change the slides until you see what's there. You should now see two yellow arrows linking the simulated injection wells to the ones in the map. And there you see that there is a groundwater flow in the direction of the River Rhine, which is to the left. And but it does not interfere with the two production wells that are in the middle, and the let's say cool water on both sides goes just outside of that. So that's important for planning. And then we look at the construction. There is a main conduit with about 5 kilometers of supply and return pipe, building connections to about 100 buildings. They are more or less completed all now after a total of 8 years of development, and those are in smaller dimensions. All the installation, including the components until into the buildings, was done by the Stadtwerke Troisdorf at a cost of about 200,000 euro for the whole conduit. That's relatively cheap, in my opinion. By the way, you see here a large solar collector field, a really large one, that you'll see later on in the background of one of the photographs from this well. The well construction, there are wells of large diameter, really large one. It's about 80 millimeter. No, not 80, 800 millimeter, 80 centimeter. The maximum production in the one area is 72 cubic meters per hour, and the other is 57. Both of these, we can call it doublets, are operated separately, and but they have an interconnection for redundancy and to allow maintenance in the one and serve the other one then. The cost of the wells is not too high. It's 120,000 euro for those wells with a large diameter, and the all the further equipment that's used in these wells. You see here pumps and pressure gauges and this. Some words about the operational experiences. By the way, this is the picture where you see the solar collectors in the background and the well in the foreground. So this is renewable energy from above and from the ground. During the startup phase, the pumping capacity was a bit too high. So the system wasn't very efficient at the beginning because the pump had to run at the lowest possible stage. But still, for 2 or 3 houses, it was too much, but you have to supply that to the houses. That changed quickly once construction of the buildings continued, and it showed nicely that this is a scalable technology. You can add more later on. The maximum required capacity was smaller because the distribution of the loads and the let's say the simultaneous use of the heat pumps in the houses was more favorable than originally thought. So the annual load was more or less as planned, but the maximum load not as high. So that's encountered now. Groundwater have their own heat pumps, but the city to the heat and the heated water to the customers. There are 2 new networks under construction, almost completed in the same city, and more projects are currently planned in the region. So the city utilities are quite happy with that technology. It works well under those conditions given here in the Rhine Valley north of Bonn. Now changing to Bonn directly. This is closer to the Rhenish Massif. You see in the background the Siebengebirge, which is a volcanic range, young one, sitting on top of the Rhenish Massif. It's a development area with office buildings, hotel, restaurant at the eastern bank of the river. It's a conversion of a former industrial area. There was a cement factory dating back to the 1850s that ceased operation in around 1980. After a lengthy planning process, construction of this new development site started in 2002. Some of the old buildings are included. You can see here in the lower left, one of the older building. There's another one just behind, so that's hidden. That was integrated. It's listed industrial structure, integrated into the new development. Now this is the plan. The Rhine is at the bottom here. So the first part was in 2002 to 2004 development, including one of the older buildings here at that end, and new construction with 2+2 wells for heating and cooling of this part. There was nothing else built at that time. Then the construction continued. This middle part here was not included into the geothermal system. This also is one of the older buildings, new ones. This has a classical heating and cooling system, and then the development from 2000. Well, this was finished 2009, this part, and 2014 this continued here. But the geothermal system was completed in 2009 to supply all this part here, the base load of this let's say development area. Again here, it's important hydrochemical indications. In this case, the simulations of groundwater flow during the pumping required to look at two neighboring open loop installations here and here. This is the 2009 part, and this the 2004 part. So to avoid any adverse interferences between the new and the old projects. Some impressions during drilling and the pumping tests. This is not the diameter of the wells. This is just a tube to protect it during the construction works. The actual diameter is a little bit smaller. It's again 80 centimeter. And there are 6 wells in this. The wells 4 and 5 have never been built. Because of the very good permeability of these wells, 28 meter deep, it was not necessary to have 8. It was fine with 6 wells, but that didn't change the numbering. So it's 4 and 5 are missing. And the heat pump with almost 1 megawatt heating capacity provide the basic cooling and heating, while there are 2 peak boilers, and there is also some additional peak cooling capacity. And we have about 180 to 200 cubic meter per hour as maximum groundwater production. It's important to see that the flow direction of the wells is reversed for summer and winter mode, so we have a warm and a cold side. And I'm almost finished with here. You see the installation. The nice thing here is that these wells, the open loop system provides heat and cold invisibly. In 2009, you could still see this is the cover of one of the wells of well number 8. Today, well, everything is landscaped, and the geothermal system with this for this fancy designer hotel is not visible in any way. Yeah, the German Post, Deutsche Post, German Mail, they issued a stamp this January showing a few down to the river Rhine from the Siebengebirge. And this is where this nice installation is located. And with that view, I thank you for your attention.
Thank you very much, Burkhard. Very interesting presentation. I would like to ask Constanze, are there any questions to Burkhard from the audience?
Yes, we do have a few questions. So one was how deep the wells in Troisdorf are, and if it was considered to change the extraction well and the injection wells.
You mean to reverse by summer and winter
yes,
operation?
to switch them.
Yeah. This is to make sure that the flow of the warm water goes always away from cooling in the vicinity in the neighboring open loop system. And that well, we also can, by doing that, optimize the temperature field around the, let's say, winter wells and summer wells. So the temperature is always a little bit lower in the wells where we extract in summer, and a little bit higher where we extract in winter time. It's one of the two basic strategies that can be used. In Troisdorf, it's just in one direction, while in the Bogen, it's in reversed.
Okay, and in the spatial arrangement, was there the possibility to change the injection well and the extraction well? Or maybe you can answer this.
I do not understand what meant with that question.
So
in the spatial.
Yeah, is there being considered in Troisdorf building the wells spatially the other way around? So maybe
it probably could have been done, yeah, but there was no reason for that. It's always also a matter to get the groundwater more direct from the production well to the consumers, and then it's not a problem to keep the temperature of the groundwater. It's not so much a problem then on the way back to the injection well.
Okay. Another question was, are the pumps for the groundwater in the project Troisdorf running all the time through the year?
Yeah, they need, because there is domestic hot water requirement, but of course there is, let's say, there are several pumps, and the pumps have stages. So in summertime there is a lower production than in wintertime. It can be adjusted.
Okay, thanks a lot. We are at the end of the first slot, so thanks a lot for your presentation.
Yeah, the other questions will be answered directly. Thank you.
Thank you very much. And I would like to come to our second presenter for today. We still stay in Germany, but we move to not so far, slightly different regions. So I would like to invite Rüdiger Grimm. He is the CEO of GeoEnergy Concept GmbH, one of the co-chairs of this session today, and he has a very long time experience in planning and designing shallow geothermal energy projects. And he is also in the management board of EGEC for shallow geothermal. And I'm looking forward to your presentation, Rüdiger. The floor is yours.
Yeah, hello, can you hear me?
Yes.
And can you see the presentation too?
Yep, confirmed.
Perfect.
Now not. You just have to go to presentation mode and then you...
Yeah, 1 second. Oh, Now I think I've got it.
Yes, great.
Yes. Perfect. So I want to speak about the development of quarters. It was just mentioned by Burkhard that this is an important task for the German market. First of all, I want to tell you some facts about the German market of shallow geothermal energy. The sales of heat pumps, ground source heat pumps, are about 20,000 per year. And with this, we are in Germany one of the main markets in Europe. And as probably some of you know, we are in a federal system. So we have different regional requirements, even for planning, for licensing, and the construction of these sites. And this makes it often not so easy. And one of the results of this fact is that we have a significant tightening of the permits. The water permits and the mining permits we need. And so this impacts to the time of the construction, to the requirements on each site we need, and so on. So, and there is also a notifiable difference among the authorities. So we have a kind of a licensing jungle. So in every state, the permits are different. So for one from outside, even from one from outside a different state, if he is not familiar with this business, it's quite difficult to understand. Third fact, we have to see the geothermal energy in context of the energy transition and especially of the heating transition. So also in this, Germany is not a big leader. So politically, it is not clear anchored. We have a very complicated funding system. So for fundings, for repayment grants, we have regional programs. So even there, you find a significant jungle. And also 1st of January of next year of 21, it will change again. And especially the allocations on the electricity price prevent the fair market access compared with gas and oil. So we have an enormous potential, but we cannot catch it in a certain way. Beside this, from the technical and scientific point of view, we have a very wide discussion about legal aspects, about certifications, about quality in drilling, about innovations in geothermal energy, about the site controlling, risk insurance, just only to touch some of our problems. And now you will see some graphs about the market. Here you see the brown ones. These are the ground source heat pumps. So since 2006, we observe more or less this status of 25,000 units per year. And meanwhile, the air source heat pumps are growing. Those ground source heat pumps maintain in this size. One of the reasons here you see Germany has the highest electricity price in whole Europe, growth of 27% in the last 10 years, and more than the half of this price comes from taxes. So this is kind of our problem in the market. But what are the current fields and future developments? Of course, we have the single family houses. There we already are in touch with our colleagues from the Netherlands with the problem of the influence to the neighbors. We have the huge market of retrofitting, which is strongly needed for the thermal transition in Germany. But there we need financial support, otherwise it will be quite difficult to enter there. We have the commercial use. There it is already established because it is heating and cooling, and this is a quite stable market. Then the quarter development, which I will speak today, it's kind of a new market, and we can find many new players moving around there. We have the grids, where we are still in a starting status with many pre-studies. Yeah, and one of these quarters I want to show you here. This is Offenbacher Main. This is near Frankfurt. So you can see the Frankfurt skyline here in the first slide behind. And on the right-hand side, this quarter, as it will be in the next 2 years. This is how we found the site in the year 2017. So those are very old buildings. Part of the site are new constructions and parts are retrofitting. But even the size of these buildings, you can see, is not something daily business for Charlotte Geothermal Energy. Here you see the red ones, this is retrofitting, and the green, blue ones, these are the new buildings. What you can see here, this is the space availability for Boral heat exchangers. So we have to keep some distance to the neighbors. Of course, we cannot use those space of the retrofitting buildings because we cannot go under it. So this is like a first start to think about how many boreholes could we put on this site. Then together with the owner, we decided to work in aisle solutions. So each constructing part or house or area has their own field. So we are not working with a grid here, but we are working with different fields and with a combination of heating and cooling. So the first task is what is the general overall heating and cooling demand. On the right hand side you see the different parts, and on the left hand side you see the total demand of the whole area, of the whole quarter. And we see, of course, and this is nice, many of you know that if we have a cooling demand, we can try to establish stable underground temperature conditions. And this is what we see on this slide. Of course, we have done different scenarios at the very beginning. And here on the left-hand side, you see the growth of the underground temperature slowly grows over the years, in this case 50 years. But what we want to have is more the second situation, a stable or a thermal balance in the underground. So here what we can see, we can use water as a brain, and we can do wonderful direct cooling with this energy scenario we see here in general. Then we started, as it is a quite big area and also not so homogeneous area, with 5 thermal response tests and 5 pilot boreholes. You see we were right, because there is even a quite interesting temperature difference of more or less 1 degree within this area. And this is quite interesting. Just to avoid this question afterwards, there is no time shift between the thermal response tests, so there is no influence of the drilling process. Then we started to do a geohydrodynamic model at the beginning. So the design went according to the general, to the total energy demand, and with the aim of a balanced temperature in the underground, which is the approach on the legal requirement in this case in the state of Hessen, because we are not allowed to have too much influence to the neighbor. I will come back to this some slides later. Now you see here we establish a thermohydrodynamic model with the software FIFLOW. So here you see the different layers, different situation for these layers. You see the Boral heat exchanger parameters, and then over this we put the energy demand for heating and cooling. And we calculate the temperature over the time. The site has a quite high dependency on the cooling demand. So you see here, if we only change 100 megawatt hours per year in cooling. There you see what will happen. Of course, it is a 0.1 degrees Celsius isotherm. This is almost nothing, but this is what they require in a legal process. Because your 0.1 isotherm goes over your site, then you have to go in a very huge mining licensing process. And this ends with this license you get after some months, which is kind of a claim. And if you own this claim, then at the very end, you own the heat, the geothermal heat or geothermal energy in this claim, and no other users is allowed to use it. And you see, our area is only here, but the claim we have is much bigger. More or less the same project we did in another state, in Saxony, in Leipzig. So it's the same size, the same process, the same heating and cooling demand. Also geological conditions in the same range of difficulty. And here we see the time scale. We see in red our project I have shown you in Offenbach, which lasted almost 12 months until we could finish the thermal response test report. In Leipzig, we got this after 3 months. So there you see what I told you at the beginning. We have really this licensing jungle. So the federal states operate in a very different way to license those projects. Here you see what happens in this area in Offenbach this year. Of course, to make it a bit more difficult, there are also piles within these buildings. So the horizontal connection versus the piles, which are by far much more important for all the architects. It's quite a challenging process for the planners and for the drillers. We have also to consider certain monitoring. So we have some measuring points, in total 4 measuring points, where we can measure the underground temperature. And this is what you see in my final slide, development of the underground temperature over the time and over the depth. So this is what the geological survey requires to see if there is an influence from the site to the neighbors. So you have to demonstrate that your geothermal model was right in a certain way. Okay, and this is so what will happen in the next years. I'm finished now with my presentation. Thank you for your presence, and if I still have time for questions, here I am. No time for questions, I see.
No. There is time for questions. So okay. Well done. Thank you very much, Rüdiger. We have 6 minutes for questions. So I would like to ask Constanze, are there any questions from the audience?
So we have one question. What about thermal activated piles for the building?
Yeah, we considered this option at the very beginning, and what we learned there is that often people say, okay, if you have piles there, then why don't you do a thermal activation? But in the daily life, this is a very complicated process because it brings you first of all a delay in the time scale. Second of it is not cheaper than to build Boral heat exchangers. Yeah, and there are also certain risks because you never know the percentage of the piles who will really get in work. But I hope we will hear other experiences from Austria regarding this.
Okay, one question was how are you monitoring the downhole temperatures in the monitoring boreholes with fiber optics or something else?
No, these are open wells with a small diameter, 2 inch. and we can always insert temperature sensors in aspect of a profile over the depth. And during the whole year, there are sensors inside in a defined depth. I don't know it exactly, and those sensors are logging the temperature all over the time.
Okay, another question was if the FeeFlow software was mandatory or if another software could be used.
Yeah, this is an interesting question for the whole German market. There are not so many players and not so many software options you have, but usually in Germany, everything which regarding this is modeled by FeeFlow. It is not mandatory, but it is mandatory to demonstrate your thermal influence to the neighbors. And we are using FeeFlow, but we are also thinking about open source software options.
Okay, then another question was, which is the average depth of the wells and how long does it take to complete it?
The average depth is 120 meters on one side and 100 meters on the other side. This has to do, or it depends a bit on the energy demand. We have to say that the underground temperature here with 13 to 14 degrees Celsius is quite high. And the cooling part is a very important, also economical part in this project. So to go deeper there would have been possible, but it would not have given us economical benefit, because then we could not cool it much.
Okay, and then the last question, is the thermal monitoring required by the authorities?
It is required and it is crazy.
So thank you very much, Rudi. We have 1 minute left. I would also like to ask you one question. You mentioned about the Offenbach example that you have individual fields of bolted exchangers. They are not connected to a grid. Why was this decided, and are these fields operating on different temperature levels during the year?
To start with your second question, of course, we cannot avoid that they will work in different temperature levels, but the level will not be that high, because let's say the general demand will be more or less the same. The decision was taken by the owner, and this is also a very simple legal reason, because he never knows when he will sell one part to a next owner. And in this case, if they are connected to a grid, it will cause some dependency, what they tried to avoid. This is the simple reason that there are different fields.
But wouldn't it make sense to engage some kind of a operator, some kind of a business operator of such systems, that you decouple it from the real estate developer?
Of course. But the owner, the current owner, yeah, we have also to say that the owner it's not a very easy one. In these 3 years, the owner has changed 3 times.
I see.
And now one of the owners is an energy operator. So there is an idea behind, but never with this time scale to think what will happen there in 3 years. It's a pity, because it would make sense, absolutely.
Yep.
But that's the daily life of the of this private equity business.
Okay, so thanks a lot, Rüdiger. And we now move away from Germany, go to the north, to Finland. And we have Jan Herren speaking about experiences with deep boreholes in Scandinavia. And Jan is working at the Rototech company. He's here country manager and promoting carbon neutrality. He was before many years engaged in Lassila Tikanoja as circular economy and development manager, and he's also a member of the Club of Rome, the national chapter. So the floor is yours, Jan, and I'm looking forward to your presentation. Thank you very much.
Great, thank you, Gregor. Thanks for letting me this opportunity to talk about our experiences with the deep boreholes in Scandinavia. So I have to coordinate it with Constance because I don't have any I can't move the slides. So Constance, let's go forward. Next slide, please. So a little bit about the agenda. So a little bit about Rototech and a few things about environmental politics in Nordic countries, something about drilling techniques, what we use and how we have streamlined it, and geoenergy as an investment also, and trends in Scandinavia, and then we go to some success stories. Let's go forward. So what we do is we deliver geoenergy fields for ground source heating and cooling, especially for large properties and industries, and of course we provide consulting for geoenergy projects. And the next slide, our mission is to improve self-efficiency, energy self-efficiency, of course, and our vision is to provide the best customer experience in the energy sector. And so we were founded in 2007 in Finland, and to challenge an old-fashioned way of doing and thinking in the industry. So that marked the beginning of Rototech's path to become the largest geoenergy company in Europe. And so the growth has been, of course, organic, but also from acquisitions. Next slide. A little bit about numbers. So far we have drilled about 51,000 geoenergy wells in Nordic countries, and we have a turnover of 56 million, 100 employees, and about 200 to 300 subcontractors, and 48 modern drilling units. And a little about where we do. So here are some Rototech sites near major cities. So as we see, we are coming closer to cities and closer to city centrals. So there's a strong need for geoenergy in city centers. And as we see in the next slide, the geoenergy in Scandinavia is quite common, and especially in Sweden, a huge amount of geoenergy wells in proportion to the habitants. And next slide. Something about the main drivers in the Nordic countries. Sweden aims to be carbon neutral by 2045. Finland carbon neutral by 2035. Norway has already done the heating oil ban, so it has a huge impact on the geoenergy, and they aim to be carbon neutral by 2030. And a very interesting thing about Denmark is that Copenhagen aims to be the first carbon neutral capital by 2025. Yeah, thank you, Constance. Let's go forward. So due to our wells that we have drilled, we drill about a couple of thousand kilometers each year, and the carbon emissions saved by our wells are about 240,000 tons. And in the next slide, we see that this corresponds to over 200,000 one-way flights from Helsinki to Bangkok. So just to put things into perspective. And next slide. So a little bit about the drilling techniques. Down the hole drilling, we use 140 millimeter and 5 millimeter permanently installed steel chasing pipe, and this goes to the soil. And we have a soil layer about from 0 meters to 100 meters in Scandinavia. So we drill with the soil drill, we drill about 2 meters into the bedrock, in which we seal the casing. And we use Komacio's 450 drilling units, and we use the Atlas compressors, 35 bar compressors, which is good enough for about to depths about to 500, 600 meters. And below that, we have to use some booster compressors. and a normal 12-meter 4-axle track for transportation of the whole thing. So we have streamlined processes, high flexibility, and quick mobilization. So this ensures that we can drill about 300 meters per day per unit. So it's quite efficient. Geoenergy as an investment is about 30 to 70 euros per square meters in Scandinavia, and that compares to about 1 to 2% of the whole cost of the building. So the larger the system are, the most cost efficient they are naturally. And so the return of the investments varies from 6 to 20%. And it's, of course, it's better the profit if we have underfloor heating, if cooling is used, system optimization, system monitoring, and usage optimization. So, and a brief, we have in about 20 years we have doubled the price of district heating. So savings brought by geoenergy increases all the time. Then a special case, I lifted this up because there was some, we have 3 years now data from this, that the social and healthcare center in Järvenpää, the geoenergy that we have now in place, and we do the peaks with district heating. The cost for all this was a little over 1 million euros. And the alternative investment with the district heating and water cooling machines was 470,000 euros. So geoenergy as an investment was over 600,000 more expensive. But when we look at the energy prices, the average from the district heating and water cooling was about 170,000 euros per year, but the realized cost about the geoenergy is 83,000 euros a year. So we have over 87,000 euros a year savings with the geoenergy. And so the payback time for this additional investment is just a little over 7 years. So 14% profit. So it's pretty amazing. And that's just with current energy prices, not the future energy prices, which will go up. So a little bit about the conditions for utilization of geoenergy in the Nordic countries and in Fennoscandia, which means Finland, Sweden, and Norway. So we have suitable bedrock for making boreholes. We have a relatively cold climate, cheap electricity for the heat pumps, and very favorable laws of regulation and environmental politics for geoenergy, which allows us to have the use of geoenergy based on shallow wells is a very economically viable in Nordic countries. Iceland has more about, it's more about deep geothermal systems due to its geological properties. And Denmark has a quite deep topsoil and sedimentary bedrock under it. So it's a lot of horizontal systems and quite a lot of geothermal system. They have a milder climate and more expensive electricity, which is not so good for our kind of product. So the next slide. This is mainly about proportions. So we can see that the Sweden is leading in the in the ground source heat pump sales and in geoenergy wells. The next slide, please. So a little bit about each country's own characteristics. Sweden, as I said, is the leading country in the world for geoenergy utilization, and 10% about of all systems are non-boreholes, which means land and water circuit and open systems. In Finland, we have about over 50% of new detached houses choose geothermal energy as a form of heating. So this is the largest share in the world. And as I said, Norway has boosted because the heating oil ban has forced the alternative energy sources. So we have grown in all categories. So in all countries, economy is the main selection criteria. but environmental values are becoming more important, and installation of very large property has become more common. Here's a lot of text, but I can take a few highlights and pickups. So the Nordic heating, district heating properties will be transferred to GeoEnergy or merge GeoEnergy hybrids for several reasons. So when we talk about synergies, district heating and district cooling are a separate system without major practical synergies. And in GeoEnergy, cooling is obtained without additional investments and often and always improves the system performance. And the environmental impact, it of course in the district heating and district cooling, it depends on the fuel, but in GeoEnergy, the renewable energy it's renewable energy, and it has very low climate impact, especially if we use certified electricity. So economic is usually the main criteria, and in district heating it often varies between different companies, and in GeoEnergy we have a very high investment cost, but when we look at the life cycle, it's lowest usually. Then we can go to the next slide. So the average depths, as we have heard, the Finland, Norway, and Sweden, we have an average depth about 250 meters and deeper. And in Finland, we have this year's numbers in the large and mega segment is about 290 meters, the average depth. So since 2014, the depth has increased with about 10 meters each year. So we are going deeper all the way. Next slide. Future trends. We see an increase in hybrid solutions, GeoEnergy combined with solar, exhaust air pump, bio-oil, and of course district heating. And we see we are going deeper all the time. We have to move closer to city centers, and we are doing it more economically than before. And then we have, of course, the BTES systems, and so seasonal heat is stored in the borehole storages, for example, from waste incineration plants and industrial waste heat sources. Then I would like to lift up, we are just started a new project that involves, we are involved in a Finnish consortium developing a positive energy building in Helsinki, Finland. So a building that produces more energy that consumes. And our aim here is to make 600 to 1,000 meter deep well a commercially viable product. So this involves developing a cost-efficient drilling technique and a collector suitable for such depths. So I will keep you all informed how this goes, but we are looking forward to this. The next slide. Some references with the deep boreholes we have done the last years. We can go to the next slide. So, okay, many of you remember this from last year's presentation, but just a reminder, Manglerudjordet in Norway near Oslo, 68 holes, GeoEnergy wells, and 300 meter deep, the savings about 200,000 euros per year. The next case is Dagens Nyheter house in Stockholm, 85 wells, 300 meter deep wells, and the building itself was built in 1960, so we have to drill all the wells from the basement. So it was a remarkable project, but very successful. So GeoEnergy replaced about 75% of the district heating and cooling. Norrlands Universitetssjukhus, a hospital in Sweden, 125 wells, 250 meter deep wells, and an amazing savings, 450,000 euros per year, and a life cycle of profit of 14.5 million euros. bear with me, two more. Sokosatel Break-Collie, Finland, amazing energy savings and carbon savings, 35 wells, 312 meter deep, and they also got, with this project, they got the cooling, room-specific cooling, which is basically free because of the geoenergy wells. And then last, we have the Skansi shopping center in Turku. We got, the moment we got put the geoenergy systems on, we got a reduction of 97% of carbon emissions. So we drilled 112 350 meter wells. And the special thing about this is that this shopping center got the first platinum LEED certification also during construction. So this is this becomes more common every day. So as a conclusion, I could say that we often talk about our national resources, but I would like to lift up the geoenergy to the list. As we have heard already, we have a great crystalline bedrock for geoenergy. We have relatively cheap electricity, and when we combine that with the seasonal variation we have in Scandinavia, we get an optimal and an ideal base for providing our modern cities and society with carbon neutral sustainable energy. So this is all I have to say. The future looks very bright in the geoenergy business, and it looks brighter every day. So I'm thrilled.
So thank you very much, Jan. Very interesting presentation. First, my question to Constanze. Are there any questions from the audience?
Yes, we have two questions so far. One is, do you know the cost in euro per meter of a borehole heat exchanger which is deeper than 600 meters?
Yes, it's about, the optimum is about when we go up to 300 meters. And then when we go down from there, it depends on the technique, that if you use the air or do you do the water drilling. So it has to do with a lot of things, but there's a big variation, and that's why we are into this project. We have to find a commercially smart way to drill deeper. So okay, I'm not going to say any exact euros per meter, but you get the point.
Okay, second question is, what is the alternative heating fuel that you are usually competing against on these projects in Scandinavia?
So it's most about district heating, of course. And now we see a lot of water and air systems that goes to the small segment, to the detachable houses, and to the renovation side. So, but yeah, district heating.
Mm-hmm.
Okay, so yeah, these were the questions from the audience.
Thank you very much. Maybe one question from my side to you, Jan. So
yes.
you have the basement, you have the crystalline rock environment in Scandinavia.
Yes.
So your deep drilling technologies, how do you think, how much are they transferable to basin regions in Europe? Because you then have different geological boundary conditions.
Yes, I know, and it's something that we are looking forward to, and we are testing at the moment. So we have done some test drillings already in Germany, but those test drillings was made in crystalline bedrock. So we are keen to look into it more and more, and we will definitely do some more test drillings to get some facts.
Mm-hmm. Okay, then thank you very much for your presentation, and
Great.
We come to the last presenter before we have our coffee break. So I would like to invite Stefan Wehinger from Enercred company. He's the CEO, and he will talk about energy foundations in large buildings in my hometown in Vienna, and he brings the example of the Marina Tower. So thank you for having you here, Stefan, and the floor is yours.
Thank you, Gregor. Thank you, everyone, for being able to present our project here. Just give me a feedback. Can you see my screen?
Yes, we can see it.
All good?
Perfectly.
Thank you. Okay, let's get started. Thank you again for the invitation. So I was asked to talk about geothermal foundation components, actually. We have heard open loop systems today and, of course, drilled boreholes. We are a company, actually we are 5 companies. Just a second, doesn't work here. This is EnerCrate Group. We are 5 companies in 3 countries, Austria, the UK, and Switzerland. And we are doing geothermal energy in general. We've been founded 40 years ago. Geothermal is our business. So we love geothermal. We learned a lot in the last 40 years. We are still there. So not everything can be wrong that we did. We paid our price on some sites because we learned from scratch how to do it. But we are in business now. We are very happy. We are fully booked for the next year. It has never been as good as it's been last year, even though Corona stopped business here and there. But still, business is very good. And we love to do it. We have our experts. Geothermal is our business. So, as we heard today, we distinguish between open loop system and closed loop systems. I'm going to concentrate on everything but open loop and closed loop boreholes today. It's all about slabs, foundation elements, slurry walls or diaphragm walls, excavation support, concrete elements in general in the ground, and of course cold networks. Here's an overview of our heat absorbers or cooling injectors into the ground. We are using driven piles, board piles, hollow piles, ductile metal piles, of course geothermal probes, slurry walls or diaphragm walls, and slab absorbers. There was one question today about prices. Based on the experience we gained in the last 40 years, driven piles are by far the most easiest and cheapest way to get geothermal absorbers into the ground. We are talking about around 50% of the price of the borehole when you compare what does 1 kilowatt of capacity, extraction capacity cost. So driven piles are around 50% of the geothermal probes. Board piles, slurry walls, hollow piles, and ductile piles are at around 60 to 70%, so still 30% cheaper. And slab absorbers, I can say that it's anywhere between 80 to 90% compared to classical boreholes. As an overview, we installed about 50,000 boreholes in the last 40 years and way over 120,000 piles or slurry walls. So we have a tendency towards geostructures, but it doesn't mean that we don't use geothermal probes, boreholes, if needed. So let's look at Marina Tower in Vienna. This is a very special project. It's completely unfavorable for any kind of geothermal use. The owner of the building, they wanted it. They said, we want to be BREEAM excellent, and that's what they got. So they asked us, what can we do? And we examined various options. It's a high-rising building, 42 floors, 500 luxury flats on the Danube. Very nice building, just next or actually over an underground station. So if you live there, you can get to the city center without even crossing a street. Just go downstairs to the underground station or go for a swim on the Danube, which is just 50 meters from the building. So quite nice building. And if you're interested in that, the prices for such a luxury flat in Vienna are still comparably cheap to many other major cities in Europe. So we're talking something like 4,000 to 10,000 euros per square meter, 10,000 of course on the top floors, 4,000 euros per square meter on the lower floors, which is, compared to what we see in other big cities, still quite cheap. So the building has a very small footprint. It's only 50 by 70 meters for the 500 luxury flats, 40 plus levels. There's district heating and district cooling available just next door. So it would have been easy for the client to just take district heating and district cooling into consideration for this site. But the owner committed to maximize the geothermal system despite these unfavorable conditions. Drilling is not possible there. The footprint is too small. There's not 1 square meter that could be used for drilling. And the contractor, which got the contract from the owner of the building, committed to a dynamic building simulation, which is something I'm going to go into more detail later on. But it was actually the base information for us to find the sweet spot of this hybrid geothermal installation for this building. What did we do? We examined closed loop absorbers, slurry foundation, the slurry walls. So here there were no piles were used. There were slurry walls used as foundation elements, which was cheaper because the machines were there anyway for the slurry walls. So they used the slurry wall machines to do slurry wall foundations for the building. And we also examined the base slab of the building to be used as a thermal absorber. Also examined or investigated was an aquifer being used just next to the Danube. And after a couple of months of detailed investigations, it turned out that the slurry foundations, so not the slurry walls, and the base slabs are going to be used as absorbers for this building. So what about the construction itself? We had a very high water table, about 10 meters above the base slab. So we had 1 bar of permanent water pressure on the whole site, which doesn't make life easier for the installation. The base slab is 2.2 meters in height, and we had 5 sub-manifolds to be used at the site. So that means hundreds of watertight pipe penetrations through this base slab. We had a very constricted or confined working space. The overall working conditions were very confined and not easy because there were many construction companies on site at the same time. The collected water from the manifolds had to run back into the slab. You can see that on the right hand side on that picture. If you see the one pipe that has a 150 diameter on the very right hand side, we had to collect the water on the top and bring it back below the base slab, back to the main manifold for the heat pumps, which is something we don't do very often, but there was no other way to do it here. So adding to the hundreds of watertight penetrations from the ground source pipes, we had to do the penetrations for the main collectors. It was a hand-in-hand construction with many other contractors being on site at the same time, and the main goal was for everyone not to be stopped in their flow of works. So there was no chance that our works could hold up other contractors from doing their job. Overall, and I think that's most important, there was a strong pro-geothermal mindset from all stakeholders on site, which is important. So if they don't want you there, it's not easy to accomplish the jobs. The result, the geothermal system now covers 55% of the heating load and 67% of the cooling load of that building. We only installed about 20% of peak capacity and still managed to cover 55% of the heating and 67% of the cooling load. District heating and dry air coolers were used to cover the peaks, the missing peaks. Domestic hot water is completely covered by district heating, which makes sense, obviously. the payback time for the additional investment in the ground source heat pump system is only 7 years, which is amazing actually. If you look at these unfavorable conditions, it's amazing that you still can achieve a 7-year payback period for a site like that. The building itself reaches the highest level of BREEAM certificate that can be achieved nowadays. There's some lessons learned from that construction site. Number one, and I think most important, it's something I stress out to every new client we have, a dynamic building simulation of a more complex building is key to find the commercial sweet spot of every ground source heat pump installation. Why is that? Simply because the size of the geothermal system can be pinpointed to the optimal commercial size if you know exactly what the loads of the building is per hour. So when do I need heating? When do I need cooling? When do I need peak heating? When do I need peak cooling? And in a hybrid system, you can then find the optimum size, commercial optimum size for the ground source heat pump system. And even under unfavorable conditions, a solution including a ground source heat pump system can be found. So that's my last sentence then. Just don't take a no when you are selling ground source heat pump system. There is always a solution. It might not be the first thing the client thinks about. It's probably not the first thing the designers think about, but very often, if we go in a detailed process of investigating a site, there is a way forward for ground source heat pump installation, even if open loop or even if drilling is not possible on site. BREEAM and other certificates like the LEED certificate or EGEC certificate help to make ground source heat pump installation more feasible, simply because these certificates need a certain amount of renewable energy on site, and they help us to stay in contact with the client to argue that ground source heat pump systems are the right way forward. And if you think 10, 15 years into the future, Austria has an oil ban for heating. We are going to have a gas ban for heating in a couple of years. Same in Switzerland. Well, we're going to see what happens in Germany, but right now it's not easy there. Rudy Grimm talks about it. It's a red tape nightmare actually to do anything there, but we're going to see what the future brings. And my final comment on this, ground source heat pump is much more about an integrated, often hybrid solution rather than just putting pipes into the ground. It's not enough to put pipes into the ground or into concrete and call it a ground source heat pump system. It has to be the integrated part of the overall solution of the building. A couple of other interesting projects. We don't have the time today to go into detail. Would have loved to show you more projects, but just a couple of projects here. Mattenhof in Switzerland, 1,600 driven piles that heat and cool 600 flats near Zurich. Frankfurt 4, which is, as far as I know, the biggest and most exclusive or most expensive construction site in Europe right now. Massive slurry walls and massive piles. Couple of hundred slurry walls, couple of hundred massive 2-meter diameter piles being used there. Completely unfavorable conditions for ground source heat pump, but all stakeholders, including the client, said we go for it. We want BREEAM excellent status, and we're going to go for it. Another site, AstraZeneca in the UK, Cambridge actually, 200 boreholes, 200 meters deep each. Very nice site. They didn't want to use the 1,500 piles they had there, so we had to go with the boreholes. No problem. We like boreholes too. Overall, a very nice, very very forward-looking project for this research center in Cambridge. I think that's it. So much from Enercred from today. Thank you for listening.
Thank you very much, Stefan, for your very interesting presentation. My question to Constanze, are there questions from the audience?
Yes, we have a few. So the first one is, which numerical tools or approaches did you use for the slurry walls?
Excuse me, I didn't get that. I'm sorry.
Which numerical tools or approaches do you use to simulate the slurry walls?
Very good question. We used a tool in the past that is actually about 20 years old and did its job in the past. Now that things get more complicated, we changed over to a software tool called COMSOL, which is a multi-physics simulation tool, and we've been using that for the last couple of years.
Okay, so the example you've shown is that district heating pipes in the ground being a critical first step in making a heat pump scheme work. Do you believe this should become a collaboration between district heat companies and shallow geothermal companies?
Yes, so I would say in the last 5 years, 95% of our sites were hybrid sites. So there was always a second or a third source of primary energy for that building. Why is that? I think that's an important point to understand. If you try to sell the biggest possible ground source heat pump system, you might end up with selling nothing because it gets too expensive and the client is not willing to invest that much money on a geothermal site. If you're willing to step back and just deliver the base load of the building, something like 20, 30, 40, 50% of the installed capacity, and still deliver 80% or 90% of peak energy in kilowatt hours, you're going to win the contract, or it's easier to win that contract. And that's why we started a long time ago to actually invite others to be part of the system. District heating, district cooling, dry air coolers, hybrid coolers, whatever you want. They should be part of the system to minimize the ground source heat pump installation in a way to find the commercial sweet spot of the overall installation.
Very well. So the last question is, did you manage to get a dynamic simulation for the Astra Sinenza building, the last one you mentioned?
There must be someone from AstraZeneca there.
It's from Robin Curtis.
We did not get it, which was a pain actually. I don't want to go into detail. We are under NDA here. No,
yeah, he says no surprise.
We did not get it, and I strongly recommend dynamic building simulations for every building that's not a high-rising, a simple flat building.
Okay, thank you very much.
Thank you very much. I would like to ask one final question to Stefan before we go into the break. So you mentioned district heating for peak load supply, but how do you motivate these energy suppliers to give you a good contract? Because it's not a real big business for them. They have the infrastructure costs, but they do not sell the heat.
Well, that's probably the first thought you would have about these companies. We have seen a very different mindset, especially in Vienna. You know, they're selling. They're trying to sell whatever they can. Their approach is not anymore to sell the whole load to the building, and very often they are at peak capacity anyway. So it would mean to add additional infrastructure costs for them, and it's way better to just give every building what it needs and to sell that part than to completely give up on district heating. Even more so, Vienna starts to buy energy into their district heating system. So if we have cooling only applications, we can talk to them nowadays and sell energy from the cooling process into the heat network.
I see. I see.
So that the mindset changed.
Mm-hmm.
Probably not everywhere in Europe, but it changed.
Okay, then thanks a lot, Stefan. We will close the first part of our session, and we will now go into a break until 11:40 Vienna time, so a little bit more than 10 minutes. And I'm looking forward to welcome you all back at 11:40. Thanks. Valeria, can you give me the control of the presentation so I can just show the yeah, thanks, that's perfect. Okay, see you then.
Sehr schön alles.
So welcome back to the second part of our best practice session of the Shallow Geothermal Energy Days 2020. So I welcome you all back. We have 4 more presentations about different case studies across Europe in the next 1 hour and 20 minutes. So I would like to invite Mr. Tim Cooper to present a very interesting case study from Ireland. So I'm not so often confronted with shallow geothermal applications in Ireland, and I'm really looking very much forward to the presentation. As I learned, Tim has very long experiences in applying shallow geothermal energy since 1993, I was told, in Dublin, and I'm really looking forward to your presentation. So the floor is yours. I cannot hear you yet. I see that you share the screen, but I cannot hear you.
Can you hear me now?
Yeah, now it's perfect. Great.
Thank you.
Thank you.
So this is an aerial view of Trinity College, where my experience with geothermal started. It's in the centre of Dublin. It was founded in 1592, and when it was outside the city in estuarine wetlands crisscrossed by drains. And I joined the staff in Trinity College in 1976. I was an engineer on a small team responsible for the operation and maintenance and development of the site. And shortly after joining that team, war broke out in the Middle East, and an energy crisis resulted. Oil deliveries to the university stopped, and the electricity supplies were cut. And I was identified as the new engineer on the team, and I was asked to take charge of a critically important energy conservation program. We were asked to try and work out how to run a university essentially without any energy. And I started collecting data. The first thing I needed was data. What did we need? What were we using? And how could we find that? And I've been collecting data from 1976 right up to now. And in the course of that, we looked at all the buildings. We had 175 buildings, ranging from historic buildings to scientific laboratories. And we also looked at all the options for renewable energy, which at that time was solar, thermal, and solar photovoltaic. And we also looked at groundwater. And groundwater proved to be the most promising. Now, I'm trying to change my slide, and it's not helping. Okay, I'm on my second slide. Can you still hear me?
Yes, very well, and I see the second slide. Thanks.
Okay, so with all the data from these buildings, I was able to identify one particular building which was terribly interesting. It was the museum building. It was designed in 1854. And the data from that building showed that it was extremely energy efficient, surprisingly more efficient than many of the modern buildings. And when I went back and looked at the original design objectives, they were absolutely fascinating. It was designed as the ultimate green building 166 years ago. So we had lots of experience and evidence of how to build energy efficient buildings. Those chimney stacks, they look like chimney stacks, but they're not. They're stack effect natural ventilation devices. And there were many other fascinating features in there that were obviously designed from the outset. When we started to look at groundwater, we actually got funding to drill and test a number of boreholes, and those red X's on that map show some of the boreholes we drilled. We went through fill and various deposits, about 5 to 10 meters in depth, and then hit a dense limestone, which we proved in most cases and drilled into in some cases. We found water-bearing gravel deposits at the interface between the fill and the limestone, and some of it high yielding, up to 32 liters a second. In the course of that planning of and managing of that energy conservation program, the concept of an ideal building emerged in our minds, and it was based on our experience with the existing buildings. High thermal inertia seemed to us to be a great advantage. We wanted changing building form because we have two seasons, a heating and a cooling season. We wanted external insulation to avail of the high thermal inertia and on. The maximum use of renewable energy, we focused on groundwater. We felt we needed Met Office input to enable us to optimize the operation of these massive buildings, and on and on. We put together a proposal for constructing this based on the anticipated reduction in CO2 emissions, which were significant, and we applied to what we then called Europe for funding and secured a grant of equivalent today of €1.5 million to build this ideal energy building, low energy building. I then had to try and find a site, and strangely enough, Dublin and Ireland was in the depths of a deep recession at that time, and nobody wanted to build anything, despite being offered €1.5 million to assist. But in the middle of Temple Bar, I found a site that was available and ready to go, and that's that green patch there. Again, sitting on land near the River Liffey, on fill and limestone. We started construction in 1993, and the first step was to drill a borehole on site, and we expected to encounter an aquifer, a reasonably prolific aquifer, and we found none. The overburden was completely impermeable. So we then decided to keep drilling until we ran out of rods in the hope that we'd find a fracture zone where there would be a significant yield. But it was when we'd completed the drilling, there was virtually no yield at all. So we redesigned the system and based it on the use of a closed single borehole, 150 meters deep, 200 millimeters in diameter, and pulling water out of the top of the borehole and returning it to the bottom, and simply extracting the energy directly from the limestone itself. We tested it by running it in reverse. In other words, by trying to heat the limestone and measuring its ability to absorb heat, and we assumed that its ability to emit heat would be similar. We reran our design calculations, including dynamic simulations, and satisfied ourselves that there was just enough heat available from the borehole to heat the building. We completed it in 1994, and it was a modern building with historic technology. Can you still see me? Can you still see the slides?
Yes, very well.
Regrettably, I can't, but okay, I can now. Sorry, my apologies. I'm having technical problems here. So that's the deep borehole. We called it deep, you call it shallow. It was 150 meters deep, and the background temperature was 13 degrees. We put that slightly elevated temperature down to the solar energy because of the high surface area for roads and solar absorbing surfaces, waste heat from buildings, some of the energy migrating up from the granite, and also some deep circulation. The heating system, the building itself was designed from the outset around the requirements for a heat pump. So we wanted to be able to heat it with very low temperature circulating water. And we did that by embedding pipes in the entire structure itself and ensuring that there was no insulation on the structure. It only had exposed surfaces throughout. The heat pump was designed with a thermal reservoir as shown in this diagram. The well was producing water at 3.2 liters per second, drawn from the top and returned in the bottom, with a 6 kilowatt electric heat pump, and with this large thermal reservoir. And the plan was to put sufficient heat into the reservoir at night to avail of the cheap nitrate electricity, and then to pull it from that reservoir during the day for the building. We needed the weather forecast to ensure that we weren't heating up the reservoir unnecessarily before warm weather and vice versa. The benefit of that reservoir was it was a super device for testing the performance of everything, because we were able to use it as a stable, constant heat load because of the standing losses from the reservoir. And I won't go into the details, but when we tested everything, we tested the building, the heat pump, the borehole itself, the completed system was significantly different to what we expected. There was much greater loss. So we set about trying to correct the faults that we saw in the constructed project. And the first thing we did was we eliminated the thermal reservoir. There was a standing loss there, which is approximately equivalent to 23% of the output from the heat pump. And by doing that, we were able to eliminate delta T across the plate heat exchangers and 2 large circulating pumps. We also replaced the evaporator in the heat pump. We were concerned slightly about corrosion. There was a high essentially sulfuric acid content. We wanted a slightly higher flow, and we wanted to reduce the delta T. We also switched off the circuit in the basement floor because we found there was too much heat being lost downwards. And when we'd made all those modifications, the system operated significantly more efficiently. In fact, the running hours dropped to less than 50%. We modified the control system because we found there was no need for weather forecast because the building itself was so stable. So we now start the heat pump running at midnight, and it runs until the building reaches its set point. We have a 3-port valve in the system that enables us to deliberately reduce the COP of the heat pump and therefore prevent or avoid the risk of freezing in the evaporation. And we've been collecting data from then to now, and here are some examples. I collect the well flow and return temperatures, the heating flow and return temperatures for the entire building and for each floor, the inside air temperature at approximately 40 locations, the CO2 concentrations in the building, the outside air temperature, and electricity consumption. And that's a plot that I downloaded relatively recently. And it shows that we're maintaining inside air temperature at 21 degrees C plus or minus 1, which is a target. You can see the outside air temperature during that period varied from 8 degrees to 18 degrees. Typical winter weather, a bit warmer than it was 20 years ago. And the minimal well flow temperature is 7.8 degrees. That's a little more detail. You can see the heat pump starting off here at midnight, and it gradually pulls the temperature of the water in the borehole down to around 5 degrees. The delta T is what we're extracting from that water. It starts, as I say, at midnight, and it switches off whenever the building reaches its set point, and that happens every night. This is a shot of 11 days, and you can see, again, very consistent, very steady performance. And this is the key set of data that the owners and tenants are interested in. The entire cost for heating each apartment is 110 euros per annum using this system. I now have finished my presentation, Gregor, and thank you very much.
Thank you very much, Tim, for a very interesting presentation, and this very interesting to see the long-term time behavior. And I asked Constanze, I guess there are some questions from the audience.
So I have one question. Are there any cultural scaling processes in the borehole over time? So is there any calcium?
Calcium scaling?
Yeah.
Initially, we had a routine of backwashing the main plate heat exchanger, and we did that approximately at minimum once every year, and often a couple of times during the initial year, and we found no significant effect. So we haven't washed that in the last 15 years.
Mm-hmm. Mm-hmm. And
very nice, thank you. So I have one comment by Riccardo Brascali. So thank you for the presentation. Having studies in the museum building at TCD is indeed a marvelous design, and great to see the data collected on the green building. And I have no further questions.
I have another question. Maybe I'm just to totally understand the concept. So you have one well extracting the energy for your building. Is it a one well solution? Is it correct?
It's a single borehole, a single well. Drilled down 170 meters. We pull the water out of the top of the well, 2 meters below the water table, pass it through the heat pump, and return the chilled water to the bottom of the well in a plastic pipe that drops down inside the well. And then the water then migrates up in contact with the limestone to the top, extracting heat as it goes.
Do you have any idea about the flow velocity of the aquifer where water is extracted? So the horizontal flow velocity.
We measured the water table in that vicinity, and we know the direction. We don't know the rate, but we have got data that will enable us to calculate the recharge rate, the thermal recharge rate, because we're pulling heat out in pulses. It brings the temperature down once every 24 hours, and when we stop extracting the heat, it warms up. So the data is there, but we haven't used it for that purpose yet.
Okay, thanks a lot very much for your presentation. If there are no further questions, we will go to the next presentation. Now we will switch to Czech Republic, and I would like to invite Marek to Svačinka from Gerotop company, and Gerotop is operating in geothermal energy in Czech and Slovak republics for 20 years now, and I'm very curious to learn more about the situation in Czech Republic. So Marek, the floor is yours.
Hey, can you hear me, please?
Yes, I hear you very well, and I see your presentation.
Perfect. Good afternoon, ladies and gentlemen. I greet you from the Czech Republic. First of all, I would like to thank you for the opportunity to present our market and company. Thanks the long-term and very good cooperation with GeoERA concept, specifically with Mr. Grimm. Thank you. Sorry. Okay. I'm going to talk about references in shallow geothermal energy. I have prepared 4 references in the territory of the capital city of Prague. First project is futuristic school gym Brezany. The second is project Palace Narodny in center Prague. The follows project campus student house with energy piles, and at the end is project mathematics and physics faculty. This is historic building with a great need for cooling. I will describe the type of object and some technical values. Okay, the first project called Futuristic School Gym Brezany. This building is almost energetically self-sufficient. The total investment was 4 million euros. The total built-up area is 2,130 square meters with a volume of 20,750 cubic meters. The building is interesting not only for its shape, but also for its aluminum shell. The Hertz is a sports area 45 times 25 meters. The whole space can be divided in several parts by using electrically blinds. On the side of spectators, there is a tribune for 250 people, and there is also facilities and tools. An interesting feature of the building is the lighting. Sufficient daylight is provided thanks to the unique large sun tunnel. The diameter of the sun tunnel are 1.2 meters, and you will find 68 pieces in the hall. The layout of the sun tunnel copies the shape of the hall. And now a little about heating and cooling system. Heating and cooling system is installed under a flexible sports floor. Total 24 times 112 meter boreholes were drilled. The production of heat and cold is provided by a cascade of 2 heat pumps with a total output about 130 kilowatts. We supply 365 megawatt hour per year of heat. It covers 93% of the building's needs. And we supply 70 megawatt hour per year of cold. It covers 100% of the building's needs. Okay, that's all I have to say about this project. Let's move on to the next project, and this is Palace Narodny. The building was built in the city center in the monument zone. The building includes offices, restaurants, shops, and galleries. Interesting is this building, the Palace Narodny, was announced as the building of the year 2019. The building has 4 underground and 8 above ground floors connected to the Baroque castle. The project began in 2005 when the city of Prague sold the land to an investor for 7 million euros, and total investment was 96 million euros. According to Forbes magazine, the Palace Narodny building has the most luxurious offices in Prague, especially in terms of price. A total of 24 times 112 meters of boreholes were drilled. The drilling took place 15 meters underground, that is a few meters below the bottom of the Vltava River. Several probes are equipped with a sensor for future monitoring. Some seismograph measurements had to be made during drilling. There was no negative impact on the surrounding buildings. When measured by thermal responses, the unaffected temperature of the rock mass was 14.1 degrees Celsius, and the thermal conductivity of the rocks was measured at 2.1 watt to Kelvin meters. Okay, this is all I have to say about this project. The following project is Campus Student House. The investor of this complex is the International Campus, which will also operate within the international network, the FEES. The complex is a large student housing project in the Czech Republic, and the complex contains a total of 529 apartments. The 8th-floor building has a total living area of over 16,500 square meters. There is also a fitness center, outdoor sports court, and a large bicycle rental service. Heat and cool are used from 177 energy piles. The outer diameter for the piles is 60 to 90 centimeters, and the depth is 5 to 13 meters. 2 piles are always connected to one circuit and connected to manifolds. A total of 4 manifolds are installed. The piles have about 8 kilometers of pipes with a diameter of 32 millimeters. And the production of heat and cold is provided by a cascade of 2 heat pumps with a total output of about 130 kilowatt. That's all for this project. The last project is Mathematics and Physics faculty. The operation of the school has high demands of the cooling of laboratory instruments, lasers, microscopes, etc. The original method of cooling was using the split units with condensing units on the facades of buildings, and the cooling medium was tap water, which was then discharged into the sewer. General 22,000 cubic meter. A central cooling circuit was implemented as a new method of cooling, now only 3,000 cubic meters. Several boreholes are equipped with sensors for future monitoring. A total of 24 times 112 meters of boreholes were drilled. And the production of heat and cold is provided by a cascade of 2 heat pumps with a total output of about 270 kilowatt, and cooling capacity is 200 kilowatt. Okay, this is all I have to say about this project, and I will now allow myself a brief summary. We believe that it's possible to implement shallow geothermal in city centers. Legislation or other legal obligations are not stuck. I would like to give a few numbers at the end. See the graph shown, where you can notice that the share of ground source heat pump has been stagnant for many years, or rather slightly in the decline. Sales of air source heat pumps have doubled in the last 4 years. Unfortunately, we lost a 30% share 10 years ago. The current ratio of ground source heat pump is only 6%. Ground source heat pumps do not have an advantage in subsidy programs and do not have support in the heat pump association. Experience in recent years has been that the number of implementation is roughly the same, but the average performance is growing, which indicates the implementation on shallow geothermal system in mid-size and large buildings. Thank you for your attention. It's all.
Thank you very much, Marek. It's interesting to see that many countries in Europe faced a similar trend in a competition between air source and ground source heat pumps. So I would like to ask Constance, other questions from the audience first.
So Gregor, we will answer any questions in written form due to some translation issues.
Okay, I see. So the answers will be the questions will be answered in the chat or later on, or how is
yes,
it
they
planned?
will be answered in chat.
Okay, thanks a lot for this insight in the Czech heat pump and ground source heat pump market. So then let's directly switch to our next presentation from Denmark. So I would like to welcome Søren Andersen from Geodrilling in Denmark. Søren is also the co-founder and chairman of the board of Thermohydrodynamic Denmark, which is an institution promoting the development of collective geothermal grids in Denmark, and I'm really very interested in that topic. Also, maybe you will also speak about this, let's say, organization a little bit in your presentation. And your presentation will be about the 5th generation district heating and cooling grids for single family homes in Denmark. So welcome, Søren, the floor is yours.
Thank you. And do you see my presentation here?
No, your schedule. Yeah, now it works. Great.
Better.
Yes.
Great. Well, I can't really share my webcam. I have two, and it doesn't recognize the other one, but we'll do without. So yes, I'm going to talk about 5th generation district heating and cooling in Denmark. And what we have in Denmark is we don't have a lot of ground source heat pumps, because 64% of the houses are supplied from district heating grids. But we are working on expanding into the rural areas of Denmark where we don't have district heating, and I'll talk a little bit about that. So 5th generation district heating and cooling, I'm sure based on all the presentations today that many of you already know what this is. I particularly like an article by Boffa et al. From 2019, who have identified 40 of these grids, different across Europe in different countries. At one point, I thought I invented this, but I just came up with it, as have many other people before me in their own small communities. So it is an idea that is invented multiple times in different locations. And as we have also seen today, it has different names. Often it's cold district heating or cold network or stuff like that. And there's also the term fifth generation district heating and cooling. And I would like to suggest that we adopt a more practical and pronounceable name. And I think the choice should be Thermonet. So it's just a word. It's not a registered trademark, and it never should be. It's just a way to describe a grid like what I'm going to present today, and that you probably already know about. So the Thermonet is shared infrastructure based on individual choices. What you see a picture of here is a small Thermonet we made in Denmark. It's just 3 houses, and in Denmark, where we have 64% coverage of district heating, the main issue is what do we do in the rural areas where we have oil and gas? And our suggestion is that you build these thermonets instead of putting up air-to-water heat pumps or individual geothermal heat pumps, because there are a lot of benefits of having a shared infrastructure, but also you have the individual choice about what size of a heat pump do you need in your house, and if you want to extract or you want to supply some heat to the ground so you can cool down your house. So Thermonet is really about energy exchange with the ground. So it's very much based on shallow geothermal technology. So it's I often say you can think about it much like how nature has uses energy, like it takes energy from the sun and also has roots into the ground. And the main problem in Denmark, since we are in the Nordics, is that we have this conception that we don't need cooling. So almost nobody in district heating talks about district cooling. We have a few places in Denmark. So when a building in Denmark needs cooling, and there are a lot of them that do, we just simply put up an air-to-air heat pump or something like that. And this is a shame because, as we have seen in many projects just in this presentation, there is a great synergy when you are in contact with the ground to use it for both heating and cooling purposes. So what we have been working on is how do you create these grids, these thermonets for single-family houses. And there are 7 of them in Denmark. Of different age and with different configurations. So many of them I have made in collaboration with different partners, and the ones I've been involved in, they use closed loop boreholes. And the closed loop boreholes is by far the most expensive way to supply energy to a thermonet. But it is also one of the ways where you get the opportunity to cool down the house, and it's also one of the techniques that is possible to do almost everywhere. It doesn't really matter. Of course, as we saw in one of the other projects, when you move into the city, you have a large building, then it can become problematic. But in Denmark, we never have those kind of projects, but because usually they already have district heatings in the cities where they are building these kinds of buildings. So a lot of them have been demonstrated using closed loop boreholes. And what we are working into now is to use some of the different energy sources. So the typical characteristics is that we use uninsulated plastic pipes. And that's the main headache when doing these kind of projects in Denmark, because it's established as common knowledge that if you have pipes in the ground and they are uninsulated, then you're going to lose heat. And that's naturally because we have this long tradition of district heating. So that's the first barrier that is getting people to understand that you can extract heat from the ground. You don't always have to lose it. And the Thermonet is very much about using the ground as a geothermal buffer. So you could get energy from anywhere, wasted heat from a sewage handling company, or you could get it from industry. You get it from a lot of different places, but you still need the ground as the geothermal buffer to even out the different temperature profiles. And of course, there is the opportunity to provide both heating and passive cooling, which is a lot more interesting than the active cooling that goes on a lot of places in Denmark. Of course, a Thermonet has to be used in combination with a geothermal heat pump. And there are these multiple possible energy sources. Energy piles are fairly new in Denmark, but of course, one of the issues of selling energy piles in Denmark is that usually you need the piles for large buildings, and large buildings are situated in areas where there are almost always district heating available. So you have a strong incentive to go with what's already there. And one of the key points mentioned in an earlier presentation is also the scalability of these geothermal systems. This is where Thermonet has a great advantage, that you can go into any city and where there is no district heating, and you can start building a Thermonet with just a few houses. You don't have to have half the city engaged from day one. Of course, that depends on if you're doing open boreholes or closed, or what type of energy source you're using. So I have a number of different illustrations of a Thermonet. So this was one of the first, simply showing that you have these pipes that are connected in the ground. So a Thermonet, to qualify as a Thermonet, I would say you have to go between lots. There has to be different owners involved. And I know for a lot of you who work with individual companies about these geothermal solutions, you could imagine it would be quite a headache when you get multiple owners involved. It increases the complexity a lot, but it actually also reduces the technical complexity because suddenly you can transport energy between buildings, and you can even out different buildings' temperature characteristics. Of course, we need some kind of role, some kind of operator who can manage the grid and see to it that everybody gets their fair share and pays an adequate price. But this is actually what we have been doing in Denmark for years and years with district heating. And what happens here is that if we put a data center in the middle of this, we can remove some boreholes, the expensive component in the grid. This is of course a nice synergy to have between a data center that only has a cooling need and absolutely no heating need, and a lot of buildings that has heating need but no cooling need. And here's an illustration about energy piles. It's also, from our experience, one of the the cheapest ways to get some energy out of the ground is to put pipes into the foundation piles. And in my opinion, I think we should start putting pipes into all foundation piles and then transport the energy to where it's needed. And it's quite a task to get that kind of thinking into the district heating business in Denmark, but it's a very relevant thought that we have this extremely cheap energy right beneath our feet, and you can also deposit energy into it. It would be a shame not to make use of it. And this is a new project we're doing, a developmental project where we combine, we're building a thermal road. So we are collecting rainwater and store it in what's practically a bathtub beneath the asphalt. And here we have probes installed horizontally in the bathtub, and we have a probe beneath a sewage pipe to extract heat from, and then we combine it with boreholes that are mainly for cooling, but we also have an idea that we can recharge these boreholes during summertime. And this goes, the heat goes out to the houses where they have individual heat pumps for heating and cooling purposes. And in the summertime, of course, cooling becomes the main purpose, and we expect that we can't use the road for this purpose, but we can certainly use the boreholes for cooling. Now, some of the key learnings when you're doing a ThermoNet is that it requires a certain mindset. And I recall that one from Energrid talked about that the mindset of district heating is changing. And I think that's necessary. Of course, when the title is fifth generation district heating and cooling, it's important to notice that most district heating in Europe is third generation. In Denmark, we are fairly far along with fourth generation, but in reality, fifth generation district heating and cooling is where I think it becomes really interesting, and it's also where the geothermal, the shallow geothermal aspects comes into play. When I say it requires a certain mindset, it means that you need to think both collectively and individually. It's a hard word, not either or. So you don't just stay inside your own lot and focus on your own energy system, but you also don't go across all of the city and force everyone into the same system. There has to be the same system for different needs. So as I mentioned before, closed loop boreholes, the most expensive, and I say that as a person who lives of selling closed loop boreholes, but it's also the most available and scalable. This may be something that's different from country to country. I know Jan mentioned from Rototech that they don't drill in Denmark, and I can say that it is very hard to drill in the loose topsoil in Denmark compared to the hard sediments in the other Nordic countries. But it is manageable, and we can also demonstrate a positive economy on ThermoNets when we do drillings in Denmark. And it's the most scalable way to start a ThermoNet. And when you utilize something that is already there, of course, you lower the cost, and that could be the energy piles or from water supply. We have a heat pump coming up in Denmark where the energy source is drinking water that is cooled down. So you basically convert the drinking water grid into an energy source for a ThermoNet. It's also an interesting solution. And of course, you can instead of wasting heat, you can utilize it. But this is a chicken and egg problem. So how do you get the chicken if you don't have the egg, and how do you get the egg if you don't have the chicken? It's systemic innovation, and the solution is you choose what you want to get, and then you start doing the work. So what we have done in Denmark is that we have created a small association called ThermoNet Denmark. If I translated it, it's non-profit, it's member-driven, and it's co-created just to support the development and expansion of ThermoNet in Denmark. And our core purpose is to connect and inspire powerhouses who guide Denmark to be a true green pioneer, provides people all over the world the opportunity for better and more comfortable lives. This is of course a high-flying purpose, but we mean it nonetheless, that there is an opportunity here to become more sustainable and also have a more comfortable home with heating and passive cooling from geothermal energy and utilizing wasted heat. So what is unique about our organization is we have a very broad type of membership. most of them probably don't know a lot about geological stuff and ground source heat pumps. We have policymakers and scientists, businesses, volunteers, advisors like lawyers and tax specialists, and we have cooperatives and consultants, and even citizens engaged in our association. And this is what you need if you want to create a grid that spans across multiple lots. You need different kinds of stakeholders involved with the same mission. So we combine our individual strength to realize the great potential that Thermonet holds. So the last slide is an invitation to you from Thermonet Denmark. We see the need to have a coordinated effort. So we're very interested in co-founding an international association called Thermonet Europe, just so we can learn a lot from each other. I am so pleased to see here today so many experts in different geothermal products. It's expertise that we don't have that much of in Denmark. But on the other hand, we have a long tradition of district heating and the collaboration needed, such as energy planning and cooperative organizations and how you monitor such shared systems. So I think there is a huge potential in cooperating across Europe in a similar organization. So I've provided an email where you're welcome to write if you or your organization is interested in collaborating about that. Thank you.
Thank you very much, Søren. Very interesting, excellent presentation. As you were speaking about Thermonet, I have to, let's say, abuse my role as the chair and bring you to notice that there is a cost action currently running. It's called Geothermal DHC, so it's about the inclusion of geothermal energy into heating and cooling networks. And I think that we might have a lot of possibilities to cooperate also on a European scale. Yeah, now I would like to ask Constanze questions from the audience.
Yes, we do have a few. So the first one is, what is the heat loss from the source to the delivery in the uninsulated plastic tubes?
Well, for the most Thermonets that has been created until now, we don't see any heat loss in the pipes because we don't utilize a lot of waste heat. But we have one of our members has an interest in supplying waste heat in a pipe of 3 kilometers length, and they calculated that the loss would be for transporting 20 degrees brine. 3 kilometers, that would only cost about 2 degrees in heat loss.
Okay, thank you very much. And how big is the tank under the road for about 5 houses in the scenario you showed before?
Oh, I don't have the amount of liters for that the bathtub I called it, but it is supposed to take 200-year incidents of rainwater without having issues.
Thank you very much. And the third question is, how is the district heating industry and for example, Euroheat and Power and the DHC-ETIP reacting to Thermonet?
Well, you could say that the very first Thermonet we made in Denmark was actually made in collaboration with the Danish Association for District Heating and a district heating company. So they tested it. I find that they are very much interested in the idea when they hear about it. But what it comes down to is that when you are going to actually construct a Thermonet, there is a lot of issues about which components do you use. There are so many different suppliers for a Thermonet compared to a traditional district heating grid that it kind of put the district heating companies into a very, very new situation. And that's not particularly comfortable for those who are used to doing something that they're very, very capable of and very knowledgeable about. So there are some reservations. They really want the documentation to show that this does work and it's trouble-free. So we're working on gathering those data for them.
Yes, thank you very much. That's all from my side.
Thank you very much, Constanze. I would like to ask you one additional question. So you mentioned you can start it's connecting a small number of individual buildings in the Thermonet concept. Which concepts do you follow to let this system grow? So like kind of an organic growth, because you are more or less limited with your capacity by your pipe diameter. So are there any ideas how to expand these systems over time?
Yeah, that's a great question, because what I learned from constructing one of the thermonets is that when naturally everybody wants to optimize, but optimization is an issue when you want to build a scalable thermonet. So you have to sometimes put bigger pipes into the ground than what your current project can justify. And of course, if you look narrowly at your own project, that's a huge mistake to put bigger pipes into the ground. But if you look at the larger perspective, suddenly it becomes the best investment you could have ever made. So that's also one of the mindsets that you need to loosen a little bit up on your optimization strategies and allow for a bigger grid to come into to play at a later point.
Yep. So do you think that you need strategic partners like communities who maybe do the basic infrastructure investments?
There are different ways of seeing it, and I think that in Denmark we will see 3 different models, and actually we already have thermonets arranged in these 3 different models. One of them is that private companies, private investors goes out and owns the thermonet. There are some legal issues in different countries about how is this possible, but in Denmark we can make a legal arrangement where it's possible to have someone who owns a thermonet, just like you could own a windmill and sell the power. The next step for me to see is that the district heating companies in Denmark, they are also required by law to be non-profit, and often they are owned by their own members, their own customers. That will be the next step, that the heating suppliers, district heating companies, starts doing thermonets. And there is, in the end, there is also the possibility that it is a collaboration between a group of house owners, like for single-family houses, that it is in the area where they live, that they come together and own the thermonet. And in that case, the municipality plays a huge role, because they have to make the decision for their citizens. Otherwise, it becomes too late. And we have one municipality in Denmark, in Middelfart, who has bought a thermonet when they created lots.
Thanks a lot. Thank you very much for your final feedback. So we will come now to the last presentation of today. So I would like to invite Guus van Gelder from Netherlands, from Groen Holland company. He's also has been for a long time in the business, since 1996, on shallow geothermal energy. And Guus will today talk about the ITGBES tool, which is aims at estimating the thermal interference between borehole heat exchanger systems. Yeah, thank you for having you here, Guus, and the floor is yours.
Thank you, Gregor. Can you hear me?
Yes, I hear you very well.
Yes.
I do not see your screen yet.
Let me have a go at that.
Yep, it works great.
Okay. The one thing I cannot see now is my screen on full screen mode.
I see it on full screen mode. That
Okay,
works.
oh, then that is fine. Then okay, I think I'm all set to go. Guus van Gelder, Groen Holland, Amsterdam. Yes, we've been involved in ground source for the last 25 years, both in the Netherlands, in the UK, and also in the rest of Europe. The talk is about the IT GBES tool, which we have translated into English as the Interference Tool Ground Source Based Energy Systems. It is, of course, a Dutch abbreviation, but this would probably fit as well. What you can see here is in 2013 in the Netherlands, there was a new ground source law on the use of the shallow underground for geothermal application. There was always a law for using wells, the ETIP systems, the well-based systems. The closed loop was not regulated, and in 2013 there was a law. Before that time, you could do as you liked. And what you can see, the growth of well closed loop systems in the Netherlands, registered ones. Prior to 2013, of course, there were already something like 25, 30, 40,000 systems, but they were not registered. After that, we had registration, and you can see the growth of the systems. There are, of course, a number of regulations on the systems. You are not allowed to go into the ground at temperatures lower than -3 degrees, maximum 30 degrees. And the real essential thing is that you cannot have a greater cumulative temperature effect on your neighbors or your neighbors on you greater than 1.5 Kelvin. And this was already foreseen in the law in 2013. So you can see that with growing numbers of closed loop ground source systems installed, like for instance, as you see above in Amersfoort, but also Stockholm, and from Rüdiger, we had a small example from Dresden in Germany. Thermal interference can occur when there is congestion. And to accommodate efficient use of ground source, planning is required. The municipality is in the Netherlands responsible. That has been delegated to the municipalities. And to assist them, in people usually not trained in this sort of system, in evaluating the spatial thermal effects between old and new systems. So old are systems that are already in place and registered, and new systems, new installed systems. They need a tool that can work quickly. It should work independently, so that it is, let's say, a tool you can use on different locations and get, let's say, similar answers in a standardized manner. And this is why the methodology, the guideline, and the tool were developed. This was already in 2011, and it's been implemented in 2013 in the law. To give you an idea, what is this thermal interference? If you look at the top left-hand picture, you see a standard design, which you could use a design tool like EED. You have a design that is valid for a standalone system, so it's just for the system itself. There are no neighboring effects. Maybe that isn't necessary because you may be all by yourself, nobody anywhere near you, but that is often not the case in more congested areas. That design will compensate for the internal effects between the system boreholes, because obviously the outer boreholes have a different set of influence temperature-wise than the central boreholes. The thing is, with EED, there is some rigidity in geometry. You can select the geometry, or there are versions of, but they are all fixed geometries, fixed depth, and they provide an average fluid temperature. And this may be very well and fine if you have a standalone system to design, and that should be more than enough. If there's no groundwater flow and no other things, you could use this very well. But obviously, as you can see on the second image in the top, you can see that if you compare this to let's say a dice with a number 5, you can see the central borehole will have effects from all sides, and the boreholes on the perimeter, they have less effect than the central borehole temperature effect, that is. And you can see on the third one with the variable positions, you can see that you have a borehole, the red one in the middle, and there are other boreholes of influence on that borehole. And they're not always in the fixed geometry, so that makes it less rigid, but you have variable positions. And you could also have variable energy rates on each of these boreholes. Let's say each borehole is a house, or each borehole is or each point represents 2 boreholes for a certain house. You can see there's a difference in distance, and so there will be different relationships between the boreholes. If you use the tool, the ITGBES tool, it uses the actual X and Y borehole positions and energy loads, so the realistic positions. It calculates the cumulative temperature effects based on the loop position and on the energy load on that loop. Have you got more heating? Have you got more cooling? Have you got a larger heat pump? Do you extract more kilowatts? You can use it to compensate your designs for the negative effects by interference by other systems. So you can calculate what the effect is, and then you can compensate your design in accordance with whatever you have agreed with your client or designer. And you can optimize the ground source heat pump system for long-term efficient performance, because if you lose temperature due to your neighbors having effects on you, it means your performance in the long term will be reduced. Now I need to close this one so I can see it. In 2011, when the new law came about, it was realized that thermal interference, especially if you have, let's say, systems close to each other, may play a big role. It could lead to legal issues. It can lead to loss of efficiency. So it's something it's important to take it into account. There was a methodology required, and a tool needed to be developed. And the Ministry of Infrastructure in the Netherlands commissioned the design of a system. Obviously, to make this, it needs to be reviewed and it needs to be accepted by a supervisory body because, well, everybody, first of all, people need to agree to the methodology. People need to be assured that it's properly calculated, it's worked, and it works well enough, it is accurate enough. In 2013, the tool was documented and accepted into the SIKB, which is the National Register for tools to be used in the ground, and also the techniques, procedures, also certification and protocols. And the tool became available for the permitting procedure, which is BUM-HUM in the Netherlands, which was actually a guidance to municipalities to actually test or check whether when they were giving a permit to a system, to make sure it was up to specification. The tool was then used with nomograms, which made it a bit awkward to use. And in 2020, there has been an update to Excel-based tool for maximum of 20 systems to look at. And in 2020, there has also been an update, because there is always the question, if there is groundwater flow, can I use the system? Can I use the tool? And up to a certain point you can. And to actually to establish these conditions, to make sure this is, let's say, the amount of groundwater flow or the amount of your loops being exposed to groundwater flow, this is to actually give the validity for the use of this system under groundwater flow conditions. And that has been done as well. It's based on, the tool is based on the finite line source, and it has been validated extensively with TRT data, with V-flow numerical analysis, and also with EED, because you do not want your design, if you use the ITGBES tool, to be very different from, let's say, established models or with actual data. Since 2013, the tool has become the de facto standard in the Netherlands. And the advantage is that the municipalities can now, their technical people can now check whether when they receive a design for which a permit is required, they can see whether, let's say, the interference with the neighboring systems has been taken into account. And it gives security to the municipalities, because they know this will avoid difficulty in future. They can allow larger developments of closed loop systems to be undertaken, and it will give the homeowners also the security that they know that in 5 years, 15, 20, 25 years time, they will still have an efficient operating system, although they may have many neighbors. Now, at this moment, Gregor, I'm running into a problem. Can you hear me?
Yes. Chris,
my problem is that my slideshow will not.
Not okay.
I cannot go to the next page. This is the problem.
Okay.
So
Can you
far
try?
it's fine. It is now locked. So
yes, I can see your slides again. Maybe can you try to follow it without, yeah, on the presentation mode? Maybe it works now again. Sorry for
So
the inconvenience.
It is me sharing the screen, but I think we will manage it.
Okay, Constance, it's you. Perfect. Then.
Okay, so if I now Constance's scherm. Yeah, but omdat zij dat heeft gedaan.
Yes, Guus, you can tell Constance to click on the next slide, and then you don't need to take care about both.
Yes, the question now is, because I've had some assistance here from my much appreciated colleague Henk. Can you now again see my screen?
I'm not sure, Constance, are you still sharing your screen?
Yes, I am.
No, we see Constance's screen in a moment. And
you see Constance's screen. Now,
she can click for you.
But we see 15 new installed GSHP systems. I think that should be the right one.
Henk, even hier komen. Want nu kan ik dus niet zien wat ik aan het presenteren. Ik zie, hij moet haar scherm zien.
Maybe, Guus, for the sake of time, maybe you just speak to the slides shown by Constance. If this
yes,
is okay
but now
for you.
the situation I have now is that the thing has been reset, so I see my own presentation again. Constance, are you looking at to make sure? Because the screen I'm looking at, is that the example, the case study of the 18 systems?
Yes. So this is my screen.
Okay. Then sorry about this, but then I'm back to where I was. This is just a case study to give you an example how the tool works in practice. It is a total of 18 systems, of which 15 are new installed. You can see them on the map on the left-hand side. In the pinkish buildings, there are 15 systems. Obviously, the data is provided by the designers, and what we need is the X and Y positions of the boreholes and the loop depth for each system, the heat pump capacity, seasonal performance factors for heating, domestic hot water, and for cooling, the annual heating and cooling requirements, and the average thermal conductivity over borehole depth as used in design. This is, let's say, standard information if you're doing a design you would have anyway. Yes, please go to the following slide. Then we have 3 existing systems that were already in the vicinity, and the information is provided via the authorities. We have the municipality from which you can source this information. And we have a search radius. We use a search radius, which is currently 120 meters. And that has been, let's say, that has been under discussion, but let's say currently the 120 meters seems to be the proper search radius for the average installed systems in the Netherlands. And we get the information from the national OLO database. The OLO database is very limited, so we can only have one X and one Y position for each system. So if a system has only one borehole, you can get the exact location of the borehole. But let's say if a house has 2 boreholes, it will be the central location of the housing lot. So there is, let's say, that is not a great big problem if you're at any distance, but it is, let's say, an approximation of the X and Y coordinates. There is talk about increasing the number of potential X and Y coordinates per location, so you could actually give every single borehole an X and Y reference. Other information you have is the total SPF, which is heating and cooling SPF divided by the total energy use. It is the annual heating, annual cooling, the heat pump capacity, the length of pipe, and the depth of the borehole. So if you have one borehole of 120 meters, the length of pipe, as we define it, is 120 meters. If you have, let's say in the last example, you have a borehole depth of 120 meters, but you have 2 boreholes in this case because the total length is 240 meters of pipe. So this is the information that we get from the national database. Yes, please go on to the following. We now go to the tool itself, and this is, let's say, the data entry screen. This is where we fill in the information, the X and Y coordinates, the information we talked about on the previous page. You can see the system on the top end. Let me have a look. Well, let's say the third one, it says we're on the number, I think the number 5 system here, filling it in. So we have a total of 18 systems. For each of these systems, we fill in the information, and then we go to the following page. And this is what we get. This is an overview in the tool of all the data entered. If that's in the blue part of the that is shown. And then we go to the brown and orange part. They have calculated the specific heat extraction and injection in kilowatt hours per meter per year. So for every location or for borehole, depending on how you filled it in, it is the exact extraction, the net extraction rate, and the injection rate, both in kilowatt hours per meter per year. So if you have a system that has a net extraction, you have a greater number of kilowatt hours per meter per year in heating than you have in extraction, than you have in injection. We go to the following page. This is the output table. This is the first output table. This is where you can see the distance between all the locations you filled in. So we have 18 locations. 1 through 15 are the new locations. 16, 17, and 18 are the already existing locations. So we see this is the difference between the locations. So if you take system number 1, the distance to number 2 is 12 meters. The distance to number 3 is 20 something meters. I cannot currently read this very clearly, but you can see all the distances are there. And you can already see that the old systems, number 16, 17, and 18, are at a relatively greater distance. For instance, number 16 is already 143 meters from number 1. So that is also already outside the search radius that we use. But there are a number of houses that are within the search radius. Can we go to the next one, Constance? The next thing is the temperature output table. And this is where you can see the temperature effects between each and every borehole position or XY position. And the thing, of course, is with the thermal interference that all the temperature effects will add up. So even small temperature effects can give you quite a large total temperature effect. And what you can see here, for instance, if we look at system number 1, you can see system number 1 has no effect whatsoever on system 16, 17, and 18. They're outside the search radius. You can see on system number 1, if you look at the column number 1, these are all the effects accumulated on system number 1. Yeah, so the total effect on system number 1, I think, is 0.7. On system number 5, for instance, you can see that there is a larger effect on the system, and that is greater than the 1.5, let's say, degrees Kelvin effect that we allow in the Netherlands. And this 1.5 is an arbitrary value, but that was selected because 1.5 K loss on your source temperature on your evaporator is about 5% efficiency loss on the efficiency of your heat pump when it's generating heating. So that has been, let's say, chosen to have a threshold value. And you can see in this case with the new development that we have 5 locations where there is in excess of the 1.5 K. So what do you do with this result? You've already moved to the next slide. Thank you, Constance. The result from ITGBES, that result, you feed back to the client or to the design, and you can make your adjustments to the design. You can increase drilling depth. Yeah, that will give you a lower extraction rate per meter. You can alter the cooling or heating requirements. It means you can do more regeneration, do more cooling, or put a solar thermal panel on your roof and put heating back into the ground. Or you can relocate your boreholes, because obviously a lot of the interference will also depend on the positions of the boreholes that you've had. So with that result, you can go back to your design and improve your design. And this is what I'll show as an example on just 3 houses, because that's simpler to show. What you have here is 1 new house and 2 existing houses. Again, we have the data input into the model, into the program, and the output in the extraction rates, etc. And from the output tables on the bottom end, you can see there's the distance table with the X and Y coordinates. Yeah, so the houses are a bit closer together. And you can see the new house, number 1, has a temperature effect that's caused on this house of minus 2.6. So this house is 1.1 degree below the legal threshold, the maximum allowable threshold. So this is what you now get from this simple example. Now, if we go to the next page. If you use, for instance, EED as your design tool, yeah, your initial design criterion, you may have used, for instance, a criterion of a minimum fluid temperature in year 25. Let's say if year 25 is long enough for your calculations, you could say what I set as a threshold in my design, it's 0 degrees temperature as a minimum under peak load conditions in year 25. So in the coldest month of the year, in year 25, you run your heat pump for a number of hours, which you define as a peak load condition, and then you say, I do not want my temperature to drop below 0 degrees C. What you found here, of course, is that there is a negative temperature effect of 2.6 degrees on this system. So first of all, you have to deal with the legal limit if you want to stay within the legal limit. To meet the legal limit in your EED design, after doing the ITG best calculation, you can adjust the fluid temperature by 1.1 degree in year 25. So you raise your criterion in your initial EED design. Yeah, and that means your minimum fluid temperature is not 0 degrees C, but 1.1 degrees C. And then you can see from the, let's say from the EED results, you can see in the previous design, you had loops of 2 times 90 meters. You need to improve that temperature to stay within the legal limit. It means you could, if you don't change the positions, you have 2 boreholes, you require 2 boreholes, 2 loops of 101 meters. So to comply with the law, to have the maximum of 1.5 degree Kelvin interference, you have to adjust your boreholes to 101 meters. Obviously, you are as a designer completely free to say, look, I am still less efficient than I would have been than if I'd, let's say, been able to achieve the 0 degrees criterion in year 25. So I may want to improve this any further. Or your client may wish, for instance, that he wants an even further improvement. And then you can use this tool to actually change your EED design again for your house and raise the temperature to a level that you find acceptable. The options that you have to enhance your efficiency, you can obviously, as we've done here, increase the loop depth. That's not always necessary because you could also change your borehole position if that is an option. And that means that you can space the boreholes further apart. You can put them further apart from, let's say, neighboring systems, or you can adapt your annual energy balance, do a bit more cooling, for instance, less heat extraction or more heat injection. Now, the ITG-BEST tool, as it is, let's say, being developed in the Netherlands as a tool to be used, it can do up to 20 systems. That's either 20 systems, but it's actually 20 X and Y positions, coordinates. Can you move to the following? So the conclusions are, it is an accurate and an easy to use tool. It's very quick, especially in the past with the nomograms. That was very prone to making mistakes and also very time consuming. Once you have filled in your data, it's a matter of seconds and your calculations are done. It has been in action, the tool, since 2013. It is a proven tool and it has been extensively validated. So we know it gives very similar results to other software programs used in designs. It allows, as I said, up to 20 individual ground source heat pump systems or loops to be used. And if you are using individual systems with multiple loops, so you have one central X and Y coordinate for your location, then that system is, let's say, allowed to be to consist up to maximum of 6 loops. For that purpose, the system has been validated. Obviously, it will give you a different temperature reading very near the loops, but that is, let's say, not the use of this tool. The tool is to actually establish the effects at greater distance on neighboring systems. And there, again, it is very accurate. It is well documented, the system. So the way it has been developed, designed, how it is to be used, is very well documented. There's an international user manual is now available in English so that you can use it, this system. It's a very handy tool in designing multiple system projects. So if you have, let's say, even if you have, let's say, small systems or systems with multiple houses involved, you can compare these with each other. And you can use it very handy to enhance your EED design system. So you can use your EED as your standard design tool, but then use ITG-BESS to optimize this in situations where you're not designing an EED as a standalone system, but multiple systems in the area. It is now available as an international version. We have a starter version available with all the documentation and support for €400. There's online support, and if you're interested and would like to use it, contact Henk Witte at Groen Holland or contact me, Guus van Gelder at Groen Holland. Contact Groen Holland, and we will give you support and help, and we'll give you information. Thank you.
Thank you very much, Guus. So we are already at the end of our webinar. Maybe I would like to ask Constanze maybe one or question, which was the maybe most important, most critical one. Is there something you would like to pose to Guus?
So one question was, the tool is now available for closed loop systems. Will it be also available for open looped systems?
No. It's not available for open loop systems. Then you have to revert, as for instance, Rudiger also said, use the tools like vFlow, which is what we do as well when we look at the interaction between closed loop and open loop, because this is a tool that is designed on conductivity, and it is not with mass transport with water movement. No, it's just for closed loop systems within, let's say, an acceptable range of groundwater flow conditions.
Okay, thanks very much. So we are at the end of our session on best practices across Europe of the Shallow Geothermal Energy Days 2020. I would like to thank you all of you for attending this webinar. I think all presentations and documentation will be available soon to the audience. And I would like to remind you on our last session of the Shallow Geothermal Energy Days on this Friday, the 11th of December, starting at 10 o'clock. We will talk about research and development, and there will be a special focus on life cycle analysis. So I'm very curious and looking forward to it. And with this, I would like to thank you and say goodbye. Probably see you on Friday this week. So Valeria, are you here?
Yes.
I think we can close the broadcast.
Absolutely. I was doing it.
Okay.
Have a good day, everyone.
Goodbye.